Greetings, everyone from Stanford. I'm actually here in my backyard, very close to the foot of the Dish Trail. As Catherine said, I'm Dean of the School of Engineering. I've been Dean for a little over 3 years now, and I'm delighted to be introducing the School of Engineering's second major virtual event for alumni. And I understand we actually have over 1,100 people registered for the event coming from all over the United States and the world. So welcome to everyone. Like all of you here at Stanford, we've been spending the past few months adjusting to new ways of doing things. The large majority of us, like myself, are working from home, and we're expecting to work from home for quite some time to come. But we have been reopening some of our experimental research labs. We've been doing it with very slow and careful approach over the past many weeks, and ramping up slowly. We currently have about 100 labs that are operating at reduced capacity with strict protocols and restrictions, of course, to ensure the health of our community. Our labs in the School of Engineering do work across a wide range of research areas and activities, but it won't surprise you that there are many new projects specifically relevant to the virus, though you might be surprised to know that we actually have COVID-related projects across all 9 of our different departments and disciplines, so it's not restricted just to the bio-related areas. You can learn more by looking at our website. This summer, in addition to the research ramp up, our faculty are also thinking about new modes of teaching. We really want to continue to provide a top-notch education to our students, but most classes will be remote in the coming year. And of course, we're all finding new ways to collaborate. And I'm pleased we're finding new ways to connect with you, our alumni. You are so important to the school and the university. So thank you for joining us today. And please be on the lookout for future virtual events that will occur in your time zone and around the world. So as you're all anticipating, today we're going to focus on the great work our faculty are doing in the field of energy research. And the discussion will be led by Arun Majumdar. Arun is a faculty member in the Department of Mechanical Engineering. He has additional affiliations in the Materials Science and Engineering Department and the Department of Photon Science at the SLAC National Accelerator Lab up the road. Arun holds the J. Precourt Provostal Professorship, and he's also co-director of the Precourt Institute for Energy. In 2009, Arun was the founding director of the Advanced Research Projects Agency in Energy, which is known fondly as ARPA-E. It's a government-funded research agency that's been instrumental in funding energy-related research. So Arun has been involved in this area from a national and international perspective for a very long time. From March 2011 to June 2012, Arun was the acting Undersecretary of Energy for the U.S. Department of Energy. After Arun left Washington, D.C., and before he joined Stanford, he spent some time as Vice President for Energy at Google. Arun is a highly distinguished scientist and engineer. He's a member of the National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences. Quite an accomplishment. And just on a personal note, Arun and I co-chaired a School of Engineering strategic planning process not long after he arrived at Stanford, back when I was an associate dean, and it was a real pleasure to work with him. So I know Arun well and just have the highest respect for him. And I know you'll enjoy hearing from him today. Arun is going to talk for about 30 minutes, and then there will be a question and answer period, which will be moderated by Will Tarpey. Will is on the faculty in our chemical engineering department, and he's also affiliated with our Department of Civil and Environmental Engineering. Like all of you, Will is a fellow alum. He received his bachelor's degree in chemical engineering from Stanford in 2012, and I'm hopeful some of his classmates are here on the call. Will earned his master's and PhD degrees from UC Berkeley. Then he was a postdoctoral research fellow at the University of Michigan, and he returned to join the Stanford faculty in 2018. Will's lab focuses on the recovery of resources from waste and also sustainable access to sanitation for all. Will is one of our newest faculty members. He does great work. He's off to a great start, and I know you'll enjoy getting to meet him as well. So I'm sure in conclusion that today's discussion will be extremely interesting all around. Thank you all again for coming. We do look forward to the day we can host you for events and visits to campus. And now welcome Arun and Will.
Great. First of all, Jennifer, thank you very much for the very generous introduction. Also want to thank Will for joining me in this one. I'm sure we're going to have a great conversation. And thank you, Catherine, and the whole team behind the scenes who've made this all happen and make us look good. And I appreciate all the people who are joining. Good morning, good afternoon, good evening to all of you. I thought what I'll do is to set the stage with a brief presentation just to set the context. And I really look forward to the Q&A session after that. And I know some of you have submitted your questions, and I'm sure there'll be many more. So let me start the presentation and see if it comes online. Okay, so I hope you can see this. So let me first start by what is the issue out here and how big and daunting is the challenge, and what is the time scale that is really needed to address this challenge. First of all, I want to point out a plot of the world population over the years for the last 10,000 years. And you can see it was pretty flat, and there have been a few pandemics in the past where the population actually went down quite significantly. And then you have a massive increase in population over the last few hundred years to about 7 or almost 8 billion people today. Where is this going? Well, the world population is predicted to max out at about 11 billion people by the end of this century. And so this is we're going to add another 3 billion people, which is roughly the population of China and India put together. That's going to happen. And most of the population growth is going to be in Africa and a little bit in developing part of Asia as well. While the population is growing, the numbers are growing, have grown. What is remarkable is over the last 150 years, the per capita GDP has grown exponentially. Not just the GDP, the per capita GDP, despite the population growth, has grown up exponentially. And this has only been in the last 150 years or so. And life today is fundamentally different from what it used to be about 150 years ago. So let me give you a glimpse of that. This is what life used to be in the past. It was mostly an agrarian society. We had farms with most of the people lived in villages, and it's a rural community, some cities, but not that big as we see today. And transportation was mostly by animal power. And what we are now seeing after 150 years, after 10,000 years of this, we are seeing over the 150 years, we have electrically lit and air-conditioned homes. We can watch television in our rooms, looking at Usain Bolt run the 100 meters or 200 meters in this case. We have healthcare system that we never had before. The life expectancy has gone up from an average about 35 or 40 years to now 70 or 80 years, and increasing. We have the world's information on our fingertips, and we are transporting ourselves in cars or planes, and we still use the same term horsepower, but instead of 1 horses, we can put 100 horses in the engine of a car, or 100,000 horses in the engine of planes in a space that was unthinkable 150 years ago. This is what we call the Industrial Revolution, which is literally going from horsepower to horsepower. This has been a silent revolution going on, and frankly, this is still continuing to happen in terms of automation, and will continue to happen for many decades and centuries to come. Now, this all has been enabled by the use of energy. You take away energy and it goes away. And this is what has these energy distribution and delivery infrastructure are really the arteries and veins of modern economies. The grid, the electricity grid, which is so fundamental, this is still the same architecture of the Nikola Tesla and Thomas Edison. So I call it the Tesla Edison architecture of the grid. And we have oil that was discovered in Pennsylvania in the 1870s, 1860s. And now we have the whole history of oil in the world, which started here and spread around the world. And we have massive infrastructure to move energy from one part of the world to another part. And this has fundamentally changed and transformed the world and has enabled all the things that I talked about previously. But this has consequences, as we know. Today, fossil fuels provide 80% of the primary energy in the world. There are a few non-fossil sources, but they all add up to about 20%, although they're growing fast. And this has consequences in terms of CO2 emissions, greenhouse gas effect, and as well as global warming. How big is the effect? Well, we are trying to keep things below 2 degrees Celsius as the global average temperature rise, but that is the average. Averages don't give you the details, and the devil isn't really in the details. So you find that in the North and South Pole, the warming is higher. The air temperature has gone up on an average by 3 or 4 degrees. It has melted the ice in Greenland. The sea ice has gone down substantially. And it's not just the sea ice. Now we are finding the land ice is also going down, not just in Greenland, but in Antarctica as well. This year, Siberia is facing a heat wave that it had never seen before. You're seeing temperatures on the order of 30 to 40 degrees Celsius in Siberia. And this is just one instance. If you really look at the statistics, here is a plot of summer temperatures around the world from the 1950s and 60s. Some summers are hot, some summers are cold. But what we are seeing is the distribution of the summer temperatures is shifting to the right, and we are witnessing high temperatures, which are 4 to 5 times the standard deviation at probabilities about 10 times what was there in the 1950s and 60s. So while Siberia is in the news today, this year, some other parts will be in the news next year. And it is not surprising that we are seeing all-time high temperatures recorded ever in the last few years around the world. So this effect is going to come to your neighborhood one of these years. So this is not going to insulate anyone from these heating effects. So here's a pop quiz. Since many of you are Stanford alums, here's a pop quiz. I'm going to give you a number, and I would like you to think about what that means and what are the units of that. Don't worry, there are no grades for this pop quiz, but here we go. First number is 1. And this is the number. This is 1 degree Celsius. This is the global average temperature rise since the pre-industrial revolution levels. It's about 1.2, but its whole number is 1. The next number is 2. This is the global average temperature rise that our target, the Paris Agreement, was for 2 degrees Celsius, and that's the target. The third number is 1,000. Don't worry, this is not 1,000 degrees Celsius, but this is 1,000 gigatons of CO2, 1,000 billion tons of CO2. If you are to keep the global average temperature rise below 2 degrees, we have a budget of 1,000 gigatons, billion tons of CO2 left. The fourth number is 40. This is the rate of emission per year. Today, it's roughly around 40 billion tons of CO2 per year. Just to give you a reference of what a billion ton means, if you add up the weight of the 7.7 billion people in the world that we have today, the total weight of all human beings is less than 1 billion ton. And we are emitting 40 billion tons of CO2 per year. The final number is 25. And that is, we have roughly 20 to 30 years left, after which the emissions have to be 0 or negative. So where are these emissions coming from? They are coming from a variety of sources. This is not a single source thing. That's why the problem is so complex. Electricity and heat is only 25%. Industry is 21%. Transportation, we think, is a big emitter. It is a big emitter, but is 14%, agriculture, land use, and forestry, 24%. So this is a multidimensional problem. If you really want to address this, we have to take a multidimensional approach. So the question is, this seems like bad news. So what is the good news? Is there a good news out there? There is. And these are some energy game changes that have happened over only the last decade or two, and that where it has come to prominence. The first one is unconventional gas that is replacing coal. And gas is roughly half the emissions. You still need fuel to run the economy. And if you can replace coal by gas, which has happened in the United States and happening in other parts of the world, this is a big deal. And at Stanford, we have now a natural gas initiative that looks at upstream, midstream, downstream methane emissions, this is a greenhouse gas, as well as the international trade and the geopolitics of unconventional gas, all put together under one campus-wide initiative called the Natural Gas Initiative. The second game changer is renewables. Renewable electricity today, as the graph at the bottom, this is solar and wind. On the vertical axis is the business contract, the purchase price of electricity generated by wind and solar. Solar is the yellow, wind is the blue, and the black dashed line is the cost of electricity production from natural gas. And what we're finding this year and even beyond, and it's still going down, it's really like the Moore's law of renewable electricity, that we're going to find this to go down even more, and it become the cheapest way to produce electricity. That's a great news. This is the first time in history where we have carbon-free source of electricity at scale and being the cheapest way to produce electricity. And finally, as you all know, this is electrification of transportation, and the battery costs have come down even faster than solar. And in the next few years, it's going to reach about $100 a kilowatt hour. That's the capital cost of a battery. Why is that important? It is important because at $100 a kilowatt hour, the range and cost of electric car becomes competitive with a gasoline car without any subsidies. And beyond that, it actually gets cheaper. And as many of you know, it's lower maintenance and everything. So this is the next 20, 30 years, you're going to see a major uptake of electric vehicles. But if you think that this is enough to address climate change, you have to think again. This is such a complex and daunting challenge. We need much more. We need, in addition to all of that, grid scale storage for long duration storage. And for long duration, it has to be at 1/10 the cost of lithium-ion batteries. Lithium-ion is not going to make it there. So we need new technologies to come in. Small modular nuclear plants at roughly half the cost of what it takes today in the United States. This is the cost that you find in Korea, in South Korea. And our cost is about twice that, and we need to reduce the cost of nuclear because that is today in the United States, the largest carbon-free source of electricity. Refrigerants have a greenhouse global warming potential 2,000 times that of CO2, and leakage of refrigerants will give rise to anywhere from 10 to 40% of global warming. Buildings consume 75% of the electricity, and they're very leaky. So how about zero net building at zero net cost? Because then it scales. Industry, probably the hardest thing to decarbonize is the industrial heat for steel, concrete, petrochemical processes, and the role of hydrogen is a very important one out here. And food and agriculture, we talked about. Food wastage contributes about roughly slightly less than the US total CO2 emissions, the global food wastage. So there's a lot to be done out there. And then, of course, the global carbon management. We have much higher fluxes of CO2 due to photosynthesis than we have from the emissions. So could we leverage that and somehow to store the carbon from the atmosphere, introduce negative emissions, and bring it down and store it in the earth? Finally, as you can now see, this affects what we are going to do in the next few decades will affect not only the electricity industry, oil and gas, and the fuel industry, the transportation, the agriculture, construction. So if you think about it, this is pretty much a large segment of our whole economy, and not just the US economy, but the global economy. It's a global issue. So let me stop there and we can get into questions, but I just wanted to set the stage for the discussion of the scale and the timing and the urgency of the issue. Thank you.
Fantastic. Thanks very much, Arun. Arun has graciously left us plenty of time for a discussion. So I'll just remind you that anyone can add questions to the Q&A at the bottom right of your Zoom screen, and all of us can be upvoting those questions, and I'll be pulling from those as well as ones that came in before. So Arun, I think let's start with, you painted out a fantastic picture of the many challenges and the motivations for addressing climate change. One of the ones I think is most interesting, and it came up in some of the questions earlier, was what can we do about it? And the we goes from individuals all the way up to institutions. So maybe we can break that we down into maybe students who are deciding what to study, high school students, undergraduate students who are deciding what to study, those who are in careers that maybe don't seem, adults who are already in careers, but maybe it doesn't seem like they can work directly on climate change. What can they do as individuals? And then also what can institutions like Stanford do about climate change?
Well, let me address the let me address the student issue and the career path, because I think this is important for students. I wish I was a student right now, undergraduate, because this is such an exciting time. And Will, you and I have worked closely together in crafting a report on the new School of Sustainability at Stanford, right? And so that's been selected now as the way to go move forward for Stanford. That's a very important thing. One of the things, if you recall, Will, you and I found that sustainability in our work that we did on campus, sustainability pretty much rests in every school, every department. And it is, again, it is such a broad issue that there is no one single major that can address it. The good news is that if you want to major in law, you will find a place in this. If you want to major in education, you will find a place in this. If you want to major in public health, you will find a place in this. Of course, if you want to major in chemical engineering, as you have, Will, you will absolutely find a place in this. And so this is one of those things that this is so broad that people will find a place in addressing this. And as we have now seen, some of the big tech companies like Google, Amazon, Microsoft, Apple, they've all pledged to make themselves carbon free, and they're using their tools and their supply chain to do that. So I think this is a collective responsibility for everyone, for institution, organizations. But as for career path, the best thing I can say is for people to go to college first. It's very important that you go to get a great education, and then go on to a career, but connect it to energy, climate, sustainability. Because the next few decades, I think the next decade, I call it the roaring 20s for clean energy. And so this is very exciting. Now, that's for students. For institutions, let me just say that there are lots of discussions going on at Stanford itself as to what should be the Stanford statement on energy and sustainability and climate. I am of the belief that if Stanford should be aggressive and progressive in this area and should lead the way and have targets which are more aggressive so that it gives breathing room for many countries that don't have an economy or a modern economy to actually grow. So we should be ahead of the game in that sense. But we also should be careful in making sure that when we make a statement, it not only has an effect on Stanford, but it has a catalyzing effect on a broader ecosystem that we live in. Just to give you an example, there are different kinds of emissions. There are scope 1 emissions, there's scope 2 emissions, and scope 3 emissions. Scope 1 emissions are direct emissions, and we should be absolutely reducing that very quickly. But the most difficult ones to reduce are the scope 3 emissions, because that depends on the supply chain. If you buy stuff, if you construct a building somewhere, there's steel, concrete, and all other indirect emissions that come in. And we should have a plan for how to affect the scope 3 emissions, because that'll have a catalyzing effect on our supply chain. And every institution should be thinking this way. How do you affect scope 3 emissions? Because then it has a catalyzing effect on the rest of the world. So, so those are the kinds of things that we have to talk through. But in terms of mechanisms of how to achieve that, and we have been having a few discussions, frankly, there's a lot of discussion of why not put a carbon price, a carbon tax or a carbon standard somewhere, which will provide some discipline and a mechanism for institutions to really reach those carbon goals that we have. So it's not enough to make a statement. We also have to have mechanisms. If you are to invest in something, maybe we should require those corporations that we invest in to have a carbon public disclosure so that they actually disclose what their goals are and how much they're contributing to the emission reduction, because we should evaluate them. And once everyone starts disclosing, maybe Stanford should set the standard for that. Once people start disclosing, then having a global international carbon price becomes much easier. So I think institutions can play a very important role in catalyzing before even the government can agree on what that pricing or what that mechanism ought to be, because we could do it ourselves. So those are the kinds of things I think we could do. And individually, our biggest, lowest hanging fruit that is very hard to get at is energy efficiency. Our homes are leaky, and it's very difficult to find exactly where they are. But if you spend a little bit of time, you could reduce emissions from your home and how you live. If you eat one less day of meat, that has a big effect. So there are the personal choices you can make that has a huge effect on carbon emissions. Of course, people think that electric cars can reduce emissions. They will reduce emissions if the grid is clean. But there are other things that we don't often see on trying to insulate our home, trying to increase energy efficiency by really efficient appliances, but use them in the right way. Those are the kinds of personal choices that can go a long way.
Absolutely. Yeah, I think one thing that I was really impressed by when Arun, you and I were serving in this committee was the fact that we had, I think, 19 faculty members on this committee that started to define the structure, and they were from all 7 schools at Stanford. And there was never a discussion where someone's perspective wasn't relevant. So I think that's just a huge testament to, on a bigger scale, we really do need everyone on this very intersectional challenge. There's a few questions, and one that's in the top of the chat that's a little bit focused on technology, but also market readiness. And the idea behind it is that solar, hydro, wind energy, possibly even nuclear, you could say, have been proven to be economically viable in some contexts. So let's look further down the pipeline in some ways, farther into the pipeline. What are some of the market-ready climate, energy, and sustainability solutions that are currently underfunded and under-leveraged that with a little bit of a push could take the same trajectory as these now more established alternative technologies?
Actually, I worry about nuclear. I'm a big fan of nuclear because it is a carbon-free source of electricity. But it has to, the way our markets, electricity markets are structured, it is the price of electricity is going down because of cheap renewables. And frankly, the price is often decided by the price of gas. It's the marginal cost that is needed to address the demand. And that price is being suppressed because of availability of a lot of gas and low cost renewables. And as a result of that, it's becoming harder and harder for nuclear to survive. And if you really want to build, so the 2 issues. One is, how do you make sure that the current nuclear plants, we have about 90 something of almost 100 nuclear plants in the United States, they need to survive, first of all. They need to make enough money to be able to pay off their loans and extend their lifetime. But if you're going to build a new nuclear plant, that cost, as I mentioned earlier in my talk, has to be half of what it is today. Otherwise, it's going to be very hard to get financing. It's going to be very hard for them to survive in today's competitive electricity markets. So even though nuclear is mature, I worry that there needs to be innovation in that continuously. And frankly, right now we are seeing tremendous amount of innovations that are going on in the nuclear, frankly, in the private sector, which is terrific. And these are small modular nuclear reactors, not just the new scale one that we hear about, but many others, some of them in the Bay Area, interestingly enough. So that is something that, I think has to be there. In terms of carbon management, I think one of the biggest challenges is negative emissions. If you are to look at any study that says that, if you are to keep the temperatures below 2 degrees, every study that we have seen suggests that at some point, 2070 onwards, 2060, 2070 onwards, we need to start having negative emissions, maybe even earlier if we can. That is not trivial because CO2 is very dilute. And so one of the ways is to leverage and harness the biological, the natural CO2 cycle, where you have about 400 billion tons of CO2 that is cycled every year through our plant system around the world. Could we tweak that by 1 or 2% to really make a big difference and store the carbon in the ground? I think we need a lot of research going into that. There's a lot of interesting discussion going on direct air capture by chemical means. And I think that's expensive today. The cost is coming down, and we need to do research and create the options for that and see how much can we reduce the cost to make it viable. So those are sort of the technological arms, and there are many more. By the grid scale, I've lined it up, at the end of the things that we need to do to develop technology. But this is more than just technology. This is an issue about markets. We need a carbon price or carbon standard of some kind. I don't care what it is. Actually, I do care what it is, but frankly, at this right now, we have not very much in terms of carbon, economy-wide carbon price. So those are the kinds of things that we do need to have to really bring this to scale. It's not enough to do this in the laboratories of Stanford. It is really important to take it out of the inventions and the discoveries that we make and turn that into innovations at scale. And that would require some kind of market mechanisms to make that happen so that it's a signal, it's a predictable signal to the business community for them to pay attention to this.
Mm-hmm. Absolutely, yeah. We see the awareness increasing individually can then make a signal to companies, like you're saying, to be more transparent with their information and also to be more intentional with their innovations, right? Towards once we see that customers start valuing things. Maybe let's take that idea of scale and get a little bit out of the lab, so to speak, and maybe we can come back because there's some other questions, but I want to make sure we're kind of speaking to several audiences here. So maybe two related questions. First, how do we think about what climate change adaptation is going to look like in the global north versus the global south? Some people call this the just transition, right? In the most industrialized countries, how do we adapt to climate change versus in developing urban centers in Africa, where much of the population growth is going to be over the rest of the century? How do we address that? And if we can also connect that to the moment that's on everyone's mind right now is effects on emissions due to COVID, right? Due to shutdowns.
Right.
Are there adaptations there? Like someone in the chat was bringing up the idea of like voluntary shutdowns, like maybe a week, a month or something, or something like this, where people voluntarily shut down to temporarily reduce emissions.
Well, let me address it in a twofold answer. One is that, as I pointed out, most of the population growth and the economic growth is going to be in developing economies. So if you are to address this as a global challenge, we have to look at those regions of the world where the people want to be prosperous, and we should enable that to happen. And we should, I think it's very hard to put the burden of climate change on those economies that are trying to develop right now. Because if you look at the CO2 emissions, the history of CO2 emissions, and the lifetime of CO2 molecules in the atmosphere that is responsible for global warming is several hundred years. And so the CO2 that we have emitted during the beginning of the Industrial Revolution is still active for global warming. And if you look at the contributions, most of the OECD countries have contributed to the CO2 that is leading to global warming. So we have a responsibility to enable the rest of the world to grow, and at the same time, enable and have us reduce our emissions. But the opportunity out here is the following, that we have the infrastructure, let's say the United States, the energy infrastructure today was designed in the 20th century. And we need a 21st century infrastructure. In many parts of the world where the economy has not yet been developed, the infrastructure does not exist. And I think here's an opportunity to enable them to leapfrog into the 21st century infrastructure, as opposed to bringing the 20th century infrastructure to them. And so I think this is, I would almost look at it as an opportunity, but also a global responsibility to enable them to grow. So that was the first part of the second issue about what do we learn now that could help in the process. Actually, we have to be very careful. So if you look at the reduction emissions due to COVID-19, it's gone down by about, there was a recent report from the International Energy Agency, our emissions have gone down by 8%. And that's because oil demand has gone down by 9%, coal has gone down, renewables actually has gone up by 1%, interesting enough. But that's 8%. The question is, are we going to rebound back? We want our economies to rebound back. Are the emissions going to rebound back? The bad news is that in the 2008-2009 financial crisis, the emissions also went down, and then it went back up, and they kept along the same trajectory as before 2008. If we go back to that, we have a problem in terms of emissions. So the question we have to ask ourselves is that, could we use this crisis as an opportunity to really have sustainable innovations being brought to the market and turn around in these investments that we're making in stimulus investments that we're making? Could we use that as an opportunity to turn our economy around to becoming more clean and still have economic growth, but try to decouple economic growth from emissions growth? And I think that's the biggest challenge. And I have an op-ed that is there in the Hill that came out last month on this particular issue. How do we best utilize our stimulus? So right now, the government, the first stimulus of $2 trillion was really a survival stimulus. It wasn't really a stimulus, it was survival, because people had lost their jobs. We hope that the next tranche of stimulus is really to stimulate the economy and to create the infrastructure for the clean energy future of the 21st century. So those, and there are plenty of jobs there as well. So that, I think, is what not just the United States, but the rest of the world has to see.
Yeah, I think that leadership of what you're getting at, decoupling emissions from economic growth and economic vitality, is really critical. If I can, I'll just plug the op-ed you just mentioned. You sent it to us, and then I sent it along to my research group, and we had a great discussion about it. So I think it was sent out with the invitation, but if not, you can find it fairly easily online with Arun's name and the Hill. Great. So I think another thing that caught my attention when you were talking, Arun, especially about this just transition idea, is about the leapfrogging that can occur in some developing economies where there's not this sunk cost in frankly, obsolete infrastructure, right? Or soon to become obsolete infrastructure. And one thing that comes up in my field of water treatment is we say the same thing about sanitation infrastructure and water infrastructure. And so this is the idea that comes up a lot in terms of the water energy nexus, and kind of has been added to it, water energy food, because these are kind of intricate and interconnected systems. So there's a question here about what are some of the most promising technical solutions for agriculture and reducing emissions, especially because in the pie chart you showed for greenhouse gas emissions globally, agriculture and forestry, I think, were another quarter, 24% of those emissions.
That's a great question. And in fact, there are plenty of opportunities. Right now, if you look at as I said, if you look at the emissions by sector, food wastage, if you just look at food wastage, we waste about 30 to 40% of our food around the world. In the developed world, it's at the consumer end. We just don't eat everything on our plate. Now, when I grew up back in India, our mom used to tell us that, you eat everything on your plate, you don't leave anything. And that's my habit. And of course, I put on weight because of that. But that's a separate issue. But because of that, because of the wastage at the consumer end, we are wasting 30 to 40% in the OECD countries. In the developing economies, it is in the supply chain of food. And from the farmer to the consumer, there are no refrigerated, or the very few refrigerated supply chain. And so there's food waste, again, about 30 to 40%. And there, the price of food really matters. In the United States, the price of food, it matters, but it's not as big a fraction of our income. But in those parts, that's survival. And so addressing food spoilage and using the food that we have actually grown is kind of a low-hanging fruit, but it's not an easy problem to solve. The refrigerated supply chains, et cetera, and behavioral issues in the developed world. So that's one. The second is that, if you look at plants and crops that we have, if we could somehow figure out how to develop plants with deeper roots and with more lignin content that we can grow, not just for our crops, but for forestry, what that would do is to grab and to do it at a rate that is fast. So can we make trees grow as fast as bamboo? Bamboo is a very fast growing plant, but can we make them grow because the rate is important and have them scale in many parts of the world? So, and if you can grow deeper roots, it is well known that the degradation of carbon goes exponentially down with the depth of the soil. So if you have the deeper the roots, they will stay there for a while. So those are the kinds of things in food and agriculture, which, and there are many other aspects of it, as I said, changing from meat to meatless diet. It's good for health if you go off red meat. And if you just do it, and this is a behavioral issue, if you just do it once a week, that has a huge effect on carbon emissions.
Great, fantastic. Arun, as a follow-up to that on kind of the personal emissions, there's a question here that's about how do you see that kind of tracking of personal emissions and personal consumption playing a part in tackling climate change? Right. What can we do to kind of close the link between seeing the data and turning it into action and empowerment of individual consumers?
That's a great question. There are lots of tools on the internet of personal carbon calculators and things like that. I mean, you could use that. I mean, a simple way to look at it is how much you travel, how much and you could use your data, put that in on these websites and actually calculate how much you emit. But frankly, that's the easy part. The difficult part are the supply chain, the clothes we wear. Mm-hmm. The textile industry is roughly 8 to 10% of the global emissions of CO2, textile. So, and the food thing, those are embedded emissions that are the steel and concrete that we use for buildings. And so those are harder to calculate, but they can be. We have a whole research arm or several faculty at Stanford in Earth and School of Earth Sciences, Energy Resource Engineering that look at, and School of Engineering, they're looking at life cycle analysis. It's not easy, but it can be done. And the embedded emissions are the really difficult ones to handle.
Absolutely. Great. I think there's a question that maybe, I promise I don't think this is a plant, but it's a question about what's the current research happening on batteries, which I imagine you can speak to from your affiliation with the Precourt Institute.
Well, there are multiple kinds, right? I mean, you have lithium-ion battery still has lots of headroom. And there's tremendous research going on in material science department, up at SLAC, in School of Earth on batteries, not just batteries, the chemistry of electrochemistry of batteries, but the battery system management. We have a new initiative called Storage X, which is focused on storage broadly. A large chunk of that is lithium-ion batteries. But as I mentioned, if you really want to look at long duration storage for the grid, and you really need long duration if you want to have 70, 80% penetration of renewables on the grid, which a lot of people like to have. And frankly, it is now cost effective and scalable, but you got to have storage then, long duration storage, 100 hours, multiple days. And for that, the cost has to be much less. Lithium ion is not going to make it. And so that's a big issue. And that's a research area that many of our faculty, Each Way, Wilshu, and many others are focused on. There are issues of battery recycling, which we're not facing today, but at some point, with the amount of batteries that we're going to have, we have to figure out how to recycle them for environmental reasons and frankly for economic reasons, because there are lots of good materials, a lot of good cobalt and manganese and lithium in there that we can recover. And then I really think this is not just Stanford, but broadly as a nation, as the United States, we need to figure out how to create a battery supply chain in the United States. There'll be many there'll be roughly 100 gigafactories that need to be built in the world to supply the batteries for lithium-ion batteries for transportation. And out of those, we need to build a few in the United States so that the research that we do at Stanford and many other places has a place to go. And the feedback loop between manufacturing and markets to the science is very important for the science to be relevant. And so that manufacturing, we have a gigafactory and a few gigafactories in the United States, but we need many more. And I think it's very important to provide the supply chain in the United States.
Great, thanks, Arun. So we have just about 10 minutes left. So I want to encourage everyone, we've got a fantastic number of questions in the Q&A. I want to encourage you also to upvote them so that we can try to snowball these and nucleate them together. There's one that's interesting. That's about what do you think are the 5 most important changes the US can take to become a global leader in adaptation to climate change, given these huge challenges of scarcity of greenhouse gas emissions, of climate change that we're facing in this century?
I'm glad this has been brought up because I think there is a risk that we will exceed 2 degrees. I think 1.5 degrees is kind of baked in right now. And if you are going to reach 2.5 or 3 degrees global average temperature rise, we need adaptation and resilience, absolutely critical. So what do we need for that? We need to figure out how to provide water because we're going to see more droughts. We're going to see temperature extremes. So water is going to be a very important commodity. I know you're working on that, and that is absolutely critical. And this is going to be an issue, not just in the United States, but many other parts of the world. Drought resistance agriculture and adaptation to higher temperatures. And that's where some of the best science in biology and plant biology is going to be very important. Trying to figure out how to manage the electricity grid when you have heat waves. You saw the Gaussian distribution move to the extreme, to the right, and we're going to have heat waves. We just can't predict when it's going to happen, where is it going to happen next year or the year after that. But at some point, it's going to come and hit us. So if that's the case, the grid is going to be under immense stress because everyone's going to turn on the air conditioners. How do we manage that? So there, I can go down the line, and then of course sea level rise, and the coastal regions, and there's a lot of population in the coastal regions. So these are the kinds of things that we have to adapt. And people think it's only the heat wave. If you have an instability of the jet stream, these are called the Rossby waves, you're going to have cold waves as well, and that's also due to climate change. So it's not just the heat waves. And when you have freezing conditions for a long period of time, as we've seen for polar vortex, et cetera, that itself creates energy-related issues because you need heating. So lots of resilience issues out there. And I think we need a concerted effort, just like we're doing for energy and emissions, reducing emissions from energy system, we need a concerted effort for adaptation and resilience.
Absolutely. Yeah, this multi-pronged strategy is going to be critical as these problems start to overlap even more than they do now. So we have a couple questions, Arun, about kind of comparing different energy storage techniques, right? So and maybe we can combine them by thinking, what are the metrics you think are important to compare things like methane versus coal, or nuclear versus solar. Cost is one, but you've mentioned life cycle analysis a bit, but what are the metrics, the key metrics that you think are important when we're comparing different energy sources or energy storage techniques, especially in different contexts?
Well, certainly economics. The cost is important. The reliability of the supply is important. So which means supply chain is very important. So you can move methane from one part of the world to another part of the world by LNG tankers. We cannot do that for electricity from, let's say, Hawaii to the United States, mainland United States. We cannot do that today. So how you move energy, but you can develop electricity generating sources in Hawaii, which is local. So supply chain, very important. Cost, very important. Emissions from that, extremely important. Reliability and resilience and security of the supply. These are all factors that go in. Mm-hmm. So in fact, this is a broader statement I'll make, that whenever we look at energy related issues, you got to look at the economics and what impact it has on the economy. We have to look at the environmental impact of this. And we also have to look at the security implications of this. And any decision that we make, if it does not address one of these three, it could come to bite us back in the future. Mm-hmm. So we have to balance our decisions based on economy, environment, and security, because it is so fundamental in our economies today.
Absolutely. Yeah, and I think that multi-criteria optimization is really critical so that you don't expose yourself, like you're saying, down the road to a reliability issue because you've only optimized for the other two, for example. Okay, it is unfortunately time for our last question, but this has been an extremely interesting discussion. Maybe if I can summarize a couple of questions here. We've got a question that you hinted at this a bit, Arun, about the role of electrolysis and kind of green hydrogen production in long-term storage of renewable energy. To tail along with that, the broader question of what kind of out-of-the-box options for energy storage beyond some of these electrochemical approaches as we know them. And maybe a third part of that more broadly is what's the role of decarbonizing kind of chemical production, so to speak. Right. And to bring that back to your pie chart, industry broadly was 21%, right? And so this is something, right, of course, I think about in my discipline too. But so to summarize, what is the role of electrolysis and green hydrogen production and storage? What kind of other blue sky options are there for these approaches? And third, can we talk about decarbonizing industrial production as well?
Well, many of us feel that hydrogen is going to be a big commodity, big important issue in the future. And today, hydrogen is produced mostly from reforming of methane using steam, which has CO2 emissions. We are now witnessing a new age coming, which is electrolysis of water splitting using electricity, using renewable electricity. And that cost is coming down, and there's tremendous innovations going on, not just in the United States, but China has also innovated in bringing down the cost of the electrolyzers that are used, which is really, really important. But there are two factors out here. One is the cost of the capex of the electrolyzers, and the second is availability of cheap, renewable, carbon-free electricity. And that is coming also. So we're seeing the next few decades are going to be very important for this, carbon-free hydrogen. But you also have to realize that there's a lot of hydrogen in methane. Mm-hmm. And if there's a lot of R&D also going on in trying to do methane pyrolysis. In fact, I'm working with Matteo Carnello in chemical engineering on an ARPA-E project to do methane pyrolysis to produce carbon-free hydrogen and produce solid carbon. And that solid carbon could potentially be used for construction material or some other as a commodity. And you have two streams of products going out using methane pyrolysis. And the good thing about methane pyrolysis is that you can move LNG, you can move methane from around the world using LNG. And if you have the methane pyrolysis, you're actually moving hydrogen there. Yeah. And so that turns out to be important, but still in the R&D phase right now. So and the hydrogen is important to some extent, but perhaps a smaller extent on transportation. People think that transportation hydrogen is going to be a big deal. Well, it's going to be big deal for perhaps long haul transportation. long haul trucking, etc. But, you know, it's most of the use of that hydrogen is going to be for industrial heat.
Right.
And the use of the hydrogen for industrial heat, for steel manufacturing, for concrete manufacturing, if you could decarbonize the hydrogen for ammonia production, that's a big deal.
Mhm.
Or for that matter, for petrochemical refinery work, if you can produce carbon-free hydrogen to enable that to happen, that's a big deal. So I think we're going to see a lot of hydrogen as a commodity, not just for transportation. I think that'll be a smaller fraction, but for renewables integration, for electricity power generation, as well as for the industrial sector, which is very, very hard to decarbonize.
Absolutely. Fantastic. Well, I think we'll end it there. Of course, this is a continuing conversation, but thanks to everyone for hosting Arun and for me right in your homes on Zoom. This was a great stand-in for an in-person event.